what will I talk about? That's a good question.
Numerical algebraic geometry and I believe tropical curves.
Right, so I'm going to talk about computation of tropical curves using homotopy continuation, and that's joint work with Anders Jensen and Josephine Yu. I'm going to follow the passionate recommendation of one of the organizers and give the total board talk. I also believe that less is more. That's why we have 8 talks a day instead of a dozen. So let me...
we could just cancel your talk.
All right. That would work. But let me entertain you further. Consider a curve. It's a curve in Cn. It's a complex curve. So I should tell that this project, well, we started talking about the idea maybe about 3 or 4 years ago, and there are many people to thank for talking to us. In particular, we talked about this with Mikael Passare back in Sweden in maybe 3 years ago, and what Mikael would do, he would apply to this the following map. So suppose your coordinates here are x1 through xn. They do get mapped into log of the absolute values of x1 through xn. So you get something in the space Rn. And that something would look, well, okay. This something would be called amoeba. So we are in the world of biology here. Okay, I think I drew enough. Is there an eraser?
Right there.
Okay, got it. This one. So what you should imagine, let me draw some holes for the dramatic effect. So what you should imagine is this body in Rn, and one way to define a tropical curve, so this is called an amoeba. One way to define a tropical curve is to take, well, let's say I have an ideal defining the original curve, and let's say it's in C. I joined all these variables. The tropicalization of that is going to be the limit when t goes to infinity of 1 over t script a of I, where a of I is this amoeba I drew. Okay. So what is that set? I'm sorry?
Yes.
I'm sorry?
Log base t.
In this case, log
Well,
base
it's the
t.
same thing as taking log base t.
Yeah, it's the same thing as if you would take the if you change the base of the log. You can do this instead. Well, what happens in this picture? It sort of shrinks and moves a little bit, and maybe you get something like this. Okay, so this would be rays with integer slopes emanating from the origin. Okay, so that's what Mikael Passare would do. What Bernd Struenfels, Dan McLagan, would do in their book, mostly, is different definition. They would take T of I to be the set of W's that are in Rn, such that the initial ideal with the weight W contains no monomials. Monomials.
Could you just say exactly what A of I is? Because I got a little confused with the discussion on the W.
AI is the image of this curve. So this is a two-dimensional real object that maps into two-dimensional real thing with boundary.
And
in Rn.
which log? Yeah, the log.
Log, put your favorite base.
And you fix that and divide by 2. So it's the same map. The same map for all T, and then you.
It seems
T,
Yeah.
it doesn't change. This particular amoeba doesn't change. I'm just taking this limit,
But
set limit.
how does T play a role in A of I? Otherwise, the limit is just the constant AI.
this is
So you
a-
have to say,
No, it's the rays that go to infinity.
No,
But-
you pick out the rays that go to
Okay, try it. Try it on the computer, maybe. I've actually never tried it. So maybe just to
yeah, choice.
give a more concrete example,
So you can either change the box or just
let's do the following curve. 1 plus x1 cubed plus x squared is going to be our x2 squared is going to be our ideal, and that will be some elliptic curve in C2, and of course it maps into something like this. So you will have the slope 2, 3. I mean the ray 2, 3 given by a primitive vector 2, 3 in the integers, and here you will have minus E2 minus E1. Okay, so the way to compute this curve, well, here it's easy. You can draw a Newton polytope, and it will look like this. And you would compute the outer normal to the Newton polytope of this one equation and get all the initial ideals that do not contain monomials. In more general, and I'm going to pick another color to write it, in a more general case, you would use software by Anders Jensen. It's called GFEN, and it does it for you on small problems, on large problems, sometimes on very large problems, but on very, very large problems, it fails. So forget about this definition. Well, what we tried to do is experiment with a very, very naive idea. So remember, there is an amoeba floating around here. So I'm just drawing the boundary of it that limits to this tropical curve. So what I would do is, let's say, take one tentacle of it and try to explain this idea in pictures. Well, what a numerical algebraic geometer would do to any picture, he or she would slice it. So we would like to slice this with let's call it H, which is going to be just a set of points, capital X. I'll use capital X for these log coordinates, where X dot V is equal to C, where V is the normal to this hyperplane, and, well, for simplicity, I'm going to take an integer. What do I get in the slice? In the slice, well, this is a full-bodied thing. So in the slice, I get a segment. But if I do take two slices that are parallel, I get two segments, and perhaps I don't want to compute points, the full segments, but I would like to sample some points in the segments. So to that end, I would introduce the ideal ID small c, which is going to be I plus the ideal defined by x to the power of v minus c, where I make sure that the small c is in relationship with the big C, which is the most natural one. C, capital C, is going to be log of the absolute values. Okay, well, now I'm in a situation where I can compute. So I can compute the zero-dimensional variety, which is the variety defined by IVC. That will give me only several points. So let's say if this is my C, then it will give me several points on this slice. But then I'm going to create a homotopy that will continue C 0. So consider homotopy C of S, where S goes from 0 to 1, in such a way that the log of the absolute value of C increases or non-decreases. Then it guarantees that you stay in the same tentacle, and you would end up, well, there are some paths that lead you here. So follow the homotopy C of S. And finally, what you would do, you would just compute the differences between the endpoints. And in number 3, you would take these guys, which are vectors in Rn, and process them with your favorite technique of getting integers out of real numbers. The favorite technique we use is LLL. You can read about the paper. It's a very simple setup. So there you get your candidate rays that later we might want to do something with. So it's an experimental computation. I mean, you run it many times with many different parameters and try to get some set, which is the set of integer vectors that would generate your rays.
So Anton, the number of black paths, that's going to be the multiplicity?
Yeah, it's common. So it's sort of a multiplicity of a tentacle. There could be many tentacles, by the way, in the same direction. At this point, we are just in block number 0 of this procedure. We would like to find some suspicious rays that may be candidates for our thing. And actually, that was like on small examples. We made an undergraduate who did an RU in Georgia Tech to run small examples, and we saw that it actually worked. Henry Duon was his name, and Robert Krohn, who's in the audience, was participating in these discussions. So, okay, well, I mean, we can stop here and declare that for some values of parameters, our thing works and gives us the correct.
C of S, you compute the log. You have to compute the log at some moment. What does it mean otherwise to follow C of S? I missed that.
You do compute the log.
Okay.
Yeah, so you get the points. Right, so the picture is drawn in the log coordinates.
Okay.
Yeah, so just fill in the blanks. I have only
Yeah. Please
10
go.
more minutes to go. All right, so what do we do next? We changed the field. So instead of C here, I would consider now the ideal in the field where the coefficients are Bezoar series. So K is CT. And suppose I do get a point. Well, maybe I should redraw this picture anatomically correct. So for this particular example, let's say I get a point W equal to 2, 3. So what I want to do next is to consider curves with non-constant coefficients, tropical curves with non-constant coefficients, and do the same, slice through the point. So here I can take 1 minus 1. I guess. Yeah, that would work. 1 minus 1 as the direction. So very similarly to this setup, I can define IV C of t, which is my I plus x to the v minus C of t, where C of t is now a Bezoar series with the same valuation as where the degree of C of t is equal to, well, I mean, I would have to pick it v dot omega. Here, the degree of t has to be set to -1. There are some conventions that are floating around, but basically, this is what happens in the picture, even the valuation picture. If you pull it back, well, the fundamental theorem, the fun theorem of tropical geometry tells you that the zero-dimensional ideal in over field K would have the following property. If I take the solution to my ideal, so if I take W and compute the multiplicity of tropicalization of, let's say, some zero-dimensional ideal J, then it is equal to the number of Bezoar series solutions to my ideal. So this is the number of Bezoar series roots. Zeros, I should call it zeros. Of J with valuation with degree equal to W. So in the same manner, we would do the following. We assume that we can, well, I mean, we can always move the picture here in such a way that W is at the origin. Okay. So if I make the transformation that x goes to x t to the w or minus w, and this point of question is at 0, that means I'm considering Bezoar, I mean the Bezoar series zeros are going to have valuation 0, so they're going to start with a constant term and the terms will go up. So each solution will look like, each solution will be a solution to the, let's say if this operation is called wave, so if this operation sends J to J wave, then I want to set up a homotopy that computes the IC the other way around. IVC of S, or let's say C of T of S. When this T actually goes from, so if you remember the picture from Charles's talk, then you will have this parameter S that would parameterize a homotopy for T that goes towards T equals 0. So let's say I picked some point where my solutions are regular, where, in other words, I do get some slice of my Bezoar series, and then I want to go to 0. And if it's generic enough, then the homotopy you have is going to avoid singular points of the branch cover. Well, it's not going to avoid this point if it were singular, but that's okay. I mean, that's okay from the point of view of applied numerical algebraic geometry. Yeah, I forgot to mention that actually in full trueness, we should consider ideals in the Laurent polynomial ring because, well, taking logs of zeros is not a kosher thing. So here we do have C star to the power 2, or n. And the thing is that perhaps your variety is going to have other components than this curve you are interested in at the coordinate axis. And this junk has to be somehow ignored. So here at t equals 0, you're going to get a very singular point towards you are driving your homotopy to. And I guess, well, at the end of that homotopy, you're of course going to discover the value of your Bezoar series with valuation 0, which are constant coefficients of your Bezoar series. And that would be exactly the multiplicity of the ray. If that multiplicity is 0, you have no ray. Okay? Well, there are several. I'm going to skip the part where I explain to you how to actually stop this computation, how to stop guessing. But let me point out that the toughest part of this was application of software. We actually had to apply all numerical, well, not all, but at least 3 packages of numerical algebraic software available. And the crucial, I mean, you may think that why do we keep programming different implementations of homotopy continuation? Isn't Bertini enough? Well, there are some features that are not present in all of them. So we actually used, the crucial for this project was PHC-PEC. So when you have this situation where the other junk floats around, you want to compute the variety that you are interested in, which is a curve in the torus. And here you have to use PHC-PEC because that's, well, out of 3 things we used, that's the only one that has an implementation of polyhedral homotopies. Otherwise, we could not move on. Well, I mean, for just sampling, everything was executed inside of Macaulay 2, where we have nice interfaces to all the other things like PHC-PEC and Bertini. Bertini was particularly useful when we drove things into singular situations. Because there, I mean, the other implementations use fixed point precision, at least for now. And with Bertini, we were able to get more accurate approximations of this leading coefficients of Bezoar series giving us multiplicity. So altogether, we used all the available knowledge and software in numerical algebraic geometry to get something that would work and please one colleague of mine. His name is Stavros Garofalidis, and he is a knot theorist. So our examples come from topology and knot theory more precisely. And this is exactly the situation where some work has been done, but a lot of it stopped because we cannot, people could not get hands on this curve because it has a lot of junk at the boundary of the torus. So at the end of the day, we are hoping to compute some invariance of knots of incompressible surfaces in the complements in the complements of knots, and well, that's the upshot of this. Another upshot is certification of all of this, and John is saying stop, so I'm stopping. Thank you.
Any questions?
Yeah.
I'm curious a little bit about the instances. So when you talk about PHC pack, then you have complete intersections. Or you have
Right, so
What's a typical input? What's a typical I? An I where this works well, that's not a complete intersection.
well, it turns out that actually the examples supplied by Stavros are complete intersections. But you can use this for non-complete intersection, the same way you are using numerical algebraic for non-complete intersections in the usual settings. Moreover, the scheme doesn't need to be reduced. You can use deflation and so on. I mean, this is all under the carpet.
It's an ideal, and you have to be sure it's a curve. That's the
You have to be sure that in the torus there is a curve, yes.
I mean, can you start with like a witness set for a curve? Witness set representative of a curve, or do you need something more than that?
You need a witness set for a curve. I think that's enough. Yeah, that's enough. And that is actually the bottleneck here, because without PHCPAC we were not able to get this witness set.
Well, also, it looks like what you're following here, when you go back to the original scheme, is the intersection of that curve with a exponential hypersurface or something, right? That's the inverse image of a, or is it?
Yeah. If you push it,
Yeah.
if you push this usual hypersurface in log coordinates up, you're gonna get, you're gonna get an inverse.
Or it's just like a translation of a subtorus.
The translation of a subtorus. It is a translation of the subtorus. It is algebraic. I mean, what it amounts to is computing an intersection, a slice of the original thing with the hypersurface given to you by a binomial. That's it.
Any other questions?
So is there any hope of sort of interfacing this with GFAM?
Interfacing.
Like combining this with GFAM to compute larger things?
Yeah, so actually, I mean, Anders got involved because he's really hitting the wall with the symbolics. And, well, I mean, the symbolics fail in a big way on those examples because you cannot even produce the candidate rays. The pre-variety there is not one-dimensional for those examples that we're interested in. And the hope is that, the hope is that this is a bottom layer of computing higher dimensional tropical varieties with this technology, because you always can sort of intersect the tropical variety and can consider links that are curves, things like that.
You guys
No,
know?
it's in the paper. There is a big future developments 2-page section of all the future that could happen. Where we made way with bigger examples of knots. That's why I say there is one happy person.
Any questions? All right, thank you, Anton.